All right. Hello, everyone. Again, this is Dr. Gallenstein, and here we are at lecture number 3 already. Can you believe it? All right. Lecture number 3 is the introduction to regression analysis. After 2 lectures that would give us a statistics review and lay some of the foundation, we are finally ready to begin to do some econometrics, all right, in which we will be using regression analysis. So today, I'm going to give you really a conceptual overview of regression analysis, and then we're going to run our first regressions. That's the objectives for today, and with that said, let us go ahead and get started. Introduction to econometrics. What is econometrics? Econometrics is the use of statistics to analyze data to answer economic questions. So imagine if you wanted to know the impact of obtaining a master's degree on income in the United States, or how a development program affects small farmers in rural Guatemala. Imagine that you wanted to answer some economics related question. You wanted to develop some model of how economic factors relate to each other. Econometrics is the way that we would do that. We will use statistics and we will use regression analysis to investigate the relationship between different variables, and at times, as we'll see later in the class, actually determine whether or not particular variables are causally related. So, and we will use those methods to answer important economic questions. So, econometrics is the use of statistics to analyze data to answer economic questions. All right. Why do we do econometrics? So econometrics allows us to do or to identify a number of different things. One is it allows us to estimate statistical relationships. So this is very similar to what we were saying in the last lecture when we talked about hypothesis testing. When we were hypothesis testing, we were seeing whether or not some observed relationship between two variables. For example, we looked at education and wages in the last lecture. It allowed us to see whether or not some observed relationship between education and wages was a reflection of the true population. Econometrics allows us to do the same thing, where we can observe and study whether or not two variables are related to each other. So, for example, how does gender relate to income? How does education relate to income? How does your crop choice relate to income? How does owning an insecticide-treated bed net affect your chances of getting malaria? So we can use econometrics to estimate statistical relationships. It also allows us to test economic theories. We can propose some economic theory. For example, we can say that as prices go up, demand goes down. Here's some economic theory. We can use econometrics to test that economic theory. We can evaluate the impact of existing programs. This will be very important in the master's program. For example, identify how a fertilizer subsidy program may impact small farmers in Ghana. We can also we can predict the impact of future programs. How will an increase in educational funding affect unemployment? How will an increase in educational funding increase incomes? We can use econometrics to predict the impact of some future program. So you can see from this that econometrics is a very useful set of skills. Okay, now what do we do in econometrics? The first thing we do is we develop a model. Okay, so I've just said that the reason we do econometrics is one of which is to test some economic theory. So if we want to test an economic theory, or if we want to evaluate the impact of a program, or we just want to determine the statistical relationship between variables, what we want to do is develop a model. Okay? An economic model assumes that some phenomenon or characteristic is a function of other phenomenon or characteristics. Let's take income as our example. It's been our go-to. What we would say is we want to specify a function that describes what factors affect income. Now, if you remember from math class, a function is something that takes input values and produces some output value. And so what we're saying is that income will be a function of other variables. Income is the outcome value, and those other variables are the input variables. Okay, so let's say that an individual's income is a function of their age, their education level, their family composition, and their work experience. So what we're saying is that income is a function of these things. If we knew what these things were, we could tell you what your income was going to be. So when we say a function, we mean that it's some mathematical expression that takes input values, so in our case, age, education, family size, experience, and then gives you some outcome. So in our case, the outcome is income. All right, so income is a function. Income is a function. I've represented function here with the letter F and these parentheses. Income is some function of age, education, family size, experience. So if I know the function, then I can tell you what somebody's income will be if given their age, education, family size, and their experience. So an economic model is a very useful thing. An economic model allows us to take information and then predict other information. It allows us to take age, education, family size, experience, and then predict or generate some outcome that is, in our case, the income value. Okay, so this is an economic model. You can see that the economic model relates some value to some other values, or some variable to other variables. This function relates age to income. It relates education to income, etc. If we have a good model, then we'll do a really good job of predicting somebody's income or any other economic factor that we might be interested in. And our task when we do econometrics is to create a good model of economic variables. We want to create a good model of economic variables. We want to develop a model that as closely as possible matches the true function, the true functional relationship between income variables and the outcome variable. So that will be our task. So let's begin by defining the functional form. All right, I just said that income now is a function, is some function of these variables, but I haven't told you what the function is. The whole point is we want to develop a function that has some form so that when we plug age, education, all these variables in, when we plug those values in, that function will give us income. All right, so let's talk about this. Let's begin by defining functional form of our income model. So here's our income model, but we don't know what the function is. The functional form is the actual function itself, which it would be easiest to see by example. So here are just two kind of strange, somewhat peculiar functional forms, but I just want to illustrate what a functional form is. The functional form is the function itself. So here's an example, like I said, a strange one. Income equals 1,000 plus 30 times age plus education to the power of experience plus 10 times family size. So if this was our true model, if this is really what determined income, then what you could do is you could tell me your age, your age, you can tell me your education level, how much experience you have, and your family size, and then I would plug those values in, and it would give me your income. This is a very strange function. You would never see this. But then what about this one? Here's some other function. Okay, this one is, okay, income equals 1,000 times age times education raised to experience divided by family size. All right, another kind of a strange function. But if this was the true function, if this was really what determined someone's income, then you could take their age, education, experience, family size, plug them into this function, and it would give you their outcome. Now, like I said, these are these are not functions we would ever work with, but it gives you that idea that there is some function. All right. So with that as our foundation here, let's go on and look at a simple linear regression model. So what we're going to do when we look at a simple linear regression model is we are going to assume a particular functional form of our economic model, and we're going to assume a linear one. So let's take a look. So we want to define our functional form. A functional form is the actual function itself. The most common is a linear functional form. All right, so let's take a look at what that looks like. Income is a function of years of education only. Okay, we're going to start off simple. A simple model is a linear model. It's a linear model of only one input. It's only one input variable. All right, so then this is going to be our simple linear model. Income equals 1,000 plus some parameter, beta 1, times education. So if this is our model, it's linear. There's no exponents. And when we mean linear, we really mean that it's linear in the parameters of the model. So that means this parameter isn't squared, or education isn't raised to the power of a parameter, but the parameter is linear. Okay. Beta 1 is a parameter, so we call it a parameter. In this case, it's the slope of years of education. It tells us how much income will increase if education increases by 1 year of education. As we write the model, we don't know what beta 1 is. But if we did, our model could predict people's income given their education. All right, so we have some model. Its income as a function of education, and it has a parameter, some unknown value. If we did know that value, then all I would need is for you to give me your education level, and I could tell you what your income was. All right, so this is a very simple function, very simple function. Let's get an idea a little bit better of what this looks like. So what we're saying is that income is a linear function of education. So a linear function is just a straight line. All right, so here we go. We got a graph, and we've got income on the y-axis. We've got education on the x-axis. So income measured in dollars, let's say, and education measured in years. All right, and we're saying that income is a linear function of education. That means it's a straight line. As you increase education, you increase income by a fixed amount. Every increase in education increases your income by the same amount, and so there's a linear line. If education equals 0, then income is 1,000. All right, we see that here. Here's our function. If education equals 0, so you plug 0 in, beta 1 times 0 is 0, income would equal 1,000. So we come back here, education equals to 0, income equals 1,000. And then it's increasing. It's increasing by some fixed amount. We call that increase the slope. Beta 1 equals the slope. It is the change in income given a change in education. So you increase education by 1 year, you will increase income by the slope, by whatever this slope is. That means beta 1 tells you how much your income will increase if education increases by 1 unit, so 1 year. All right, let's take a look here. So slope is the amount that income will increase given a 1 unit increase in education. So for example, imagine that the slope is 5. That means that if education goes up by 1, the income will go up by 5. All right, so this is some very simple linear model of income. But now we've got to say, okay, is our model true? Is that really how income works? Is it really true that if you have no income, you earn $1,000, and for every year of schooling you have, you earn beta 1 more dollars? Is that true? Is it a true model? So we know whether our model is good, whether it's reasonably close to true, by how well it describes real data. Well, would our model actually describe real income patterns and how income is influenced by experience? Okay, I've said education here, so let me change this. Education. All right. So would our model actually describe real income patterns? How income is influenced by education? Almost certainly not. If you went out and you talked to a bunch of people and you asked them how, what their income was, and you asked them how many years of schooling they had, you would not find that their income was a perfect linear function of their years of schooling. All right, so almost certainly not. Realistically, experience, all right, sorry, I need to change this to education. Education, all right. Realistically, education is not the only factor that will influence someone's income. Income will be influenced by a lot of factors, okay? But we're only going to look at one factor today. All right, so let's take a look at this. So realistically, income is not going to be a function of just education. All right, what we're looking at here is what's called a scatter plot. Each one of these little dots indicates some amount of income given some level of education. So each one of these little dots is a data point. If we went out and we collected data on people's incomes and their education level, we went out and collected data. Every person would have some different combination. Some person is making $60,000 a year and they have 5 years of education. And somebody else is making $130,000 a year. Let's see this person here, $130,000 a year, and they have 12 and a half years of schooling, etc. So we've got all these different data points for all these different individuals. And you can see that, okay, there is some relationship. As education goes up, income seems to go up, right? There's a trend. As education increases, income increases, all right? We see the trend. But it's not perfectly linear. It's not a perfectly linear relationship. There must be other things that are affecting people's income. It's not only education. If it was only education, then all these data points would line up in a straight line. And they don't. They're scattered. They're scattered around. Now we can see there's some general relationship here. But there must be other factors that's affecting income beyond just education. All right, so let's say we plotted our linear relationship between income and education. We could take our linear function and we could graph it. Okay, we can graph it on the scatter plot, and this would give us kind of the general trend in the data. This single linear line would give us kind of the general trend that we see in this data set, in these data values. But we can recognize that this linear line, again, does not describe every single data value, every single data point. It actually will give us a pretty good idea of the trends in the data, but it doesn't describe every value. It doesn't pass through every single data point. So that means there's some difference between an individual's income and their education level. Education can't fully explain it. Okay, so then one thing we do is assume that everyone's income is a function of education and some other factor that we call an error term, where the error term accounts for every other factor that we don't have in the model. All right, so now we're expanding our model a little bit. We're saying, okay, yes, income is a function of education, but it also has some error term. We call it some error term. And this error term accounts for all the other factors that might affect income. It basically accounts for all the little differences between each individual data point and this smooth linear line. So the error, so let's say we take an income of 15 and we follow this up. Our model would say that they should have an income. So our education's 15 years, and our model says that they should have an income around $150,000 a year. Okay, sorry, all right. But the data, we've got a data point here, and this data point says they've got 15 years of schooling and $140,000 a year in income. All right, that's here. And so there's some difference between our model and the data point, and we're saying that that's the error. That's the error term. That's the error. That's accounting for all the other factors that might affect income. All right. I said the error term accounts for all the other factors that we don't have in the model. So this could be experience, household characteristics, etc. Some other set of variables, age, where you live, your location, etc. So any other factor that might affect income, any other factor that might belong in a true, realistic model of income would fall in the error term. Okay, so now here we go. We have a simple linear model of income as a function of education, and everything else is in the error term. All right, so here we go. We've just talked you through this. Let's look at it again. So the error is the difference between what I'm calling the predicted value and the real value. So the predicted value is the value that the model says should be the case, and the real value is the value that the data actually takes. So there's some error between every single one of these data points and our model. Okay, our model does a fair job of describing the general trend and the relationship between education and income, but any particular data point is going to have some error. There's going to be some difference between a particular data point and our line and our regression model, our economic model. Okay, with that said, let's take this and let's think about it in a generic form. Okay, this is a generic, simple, linear regression model. All right, we're just looking at it generically. We're going to think about this a lot. Okay, so let's take some time looking through this. What we have is that we basically have some model of some economic outcome. That's Y. Before we looked at income, now we're making it general. So Y can be anything. Income, it can be health outcomes, it can be, it can be demand, it can be any number of things. Okay, it's some economic variable that we're interested in. All right, this Y we can call it the dependent variable, outcome variable, explained variable, response variable, regressand. There's a bunch of different names for it. You'll hear me use dependent variable and outcome variable most often. So if you hear me say dependent variable, that means Y. Or if you hear me say outcome variable, again, that means this Y. It's the variable on the left-hand side of our model. It's usually the variable that we're trying to explain. If we're trying to explain income, then this is where income would go. I say I want to have a function that describes or that defines what values determine income. Income would be my dependent variable, my outcome variable, the variable that I'm interested in, the variable that I want to explain. That would be this y. All right. And in our economic model, we're saying that y equals something. It equals some function. All right. It equals some function of another variable, x. All right. We're going to look at this one next. So x is some other variable. Before we said it was education, but now we're making it general. We're saying that y is some function of x. X is some other variable. So we call x, we call it an independent variable, or an explanatory variable, or a control variable, or a predictive variable, or a regressor. There's a lot of names for it. You'll mostly hear me use the word dependent variable or explanatory variable when we talk about x. X is some variable that we want to know the relationship between y and x. Like in our example before, we wanted to know the relationship between income and education. We wanted to know, okay, how much does your income go up if you have one more year of schooling? That might be information that would be valuable to you. How much more will you make if you get one more year of education? So we want to know the relationship between y and x. Okay, well, what is that relationship? That's captured by this beta 1, all right? Beta 1's a parameter, and we already said before, beta 1 is the slope parameter. It's the coefficient on the independent variable. So it's a parameter, or we might call it a coefficient, all right? It's a number. It starts out unknown to us, but it's a number multiplied by the independent variable. And the slope parameter gives us the slope, the relationship between y and x. Beta 1 tells us how much y goes up when x goes up by 1 unit. How much your income will go up if your education goes up by 1 unit. That's what beta 1 tells us. All right? Beta 0, or beta naught as it's sometimes called, is called the constant. Or, and I actually don't have this one in here, I'm going to add it, the constant, or an intercept term, okay? Or you might call it the coefficient on the intercept. Basically what beta 0 or beta naught is it tells you whatever value y is going to be when x equals 0. All right, it's the intercept. So it's like our linear line I showed you here before. In our initial example, beta 0 was 1,000. It's the value of income when education equals 0. All right. And lastly, the error term. Thank goodness we usually only have one name for this. It's the error term. The error term accounts for everything else that might affect the dependent variable. It accounts for everything else. So if this was education, then this is experience and ability and a bunch of other things. All right. All right, so why do we do econometrics? We're going to come back to that again. We do econometrics because we want to find out what beta 0 and beta 1 are in reality. When I say in reality, what do I usually mean? I mean what they are for the population. All right, so let's think about this. In a real population of people, there is a real relationship between income and, again, so in an earlier version of these notes, I had experience and I switched to education. So that's why you're seeing this. Sorry about that. All right, in a real population of people, there is a real relationship between income and education. We could think about it this way. There is, in reality, a function that describes the relationship between income and education. There is some real function that determines how much income people make. And that function, and it is a function of education. So there is some real relationship between income and education. There is some true beta 1. There is some true slope. There is some true value for beta 1 that will describe how much income goes up when you increase your education. So this means that there is some true or population linear model. This model, there exists some true population linear model, where income equals beta naught plus beta 1 times education plus some error term. So in the real population, there's some relationship. Well, as you know from the last 2 lectures, we never have data on the whole population. And if we never have data on the whole population, we're never able to know the true beta 1 and beta 0. We're not going to know the true ones. So, what do we do? What do? We estimate. So we estimate the linear model. We estimate what beta 0 and beta 1 are. We have to create estimates. We don't know, we do not know this equation, right? We don't know what beta 0 and beta 1 are. We don't know the true relationship between education and income. We also cannot collect data on every person in the country, every person in the whole population, to know what their income is and their education level. Education level. All right, so we can't just simply calculate what beta naught and beta 1 are. Instead, we have to estimate. We need to estimate what beta 0 and beta 1 are. All right, using sample data. So we estimate it. All right, so we're defining estimate. To estimate something is to roughly calculate or judge the value, number, quantity, or extent of something. Or a noun, an estimate. An estimate is an approximate calculation or judgment of the value, number, quantity, or extent of something. So we use statistical methods to estimate or to derive estimates of beta 0 and beta 1. We want to estimate what they are so that we can have some idea of the relationship between our dependent variable and our independent variable. All right, so let's get an idea of what this might look like. So we had our scatter plot before, right? Scatter plot of data. And now let's say that this blue line is the true linear relationship. It's the true linear relationship. This blue line is this function, our true linear model of the relationship between income and education. The slope of this blue line tells us the true population beta 1. It gives us the true value. It tells us how much income on average will increase if you increase your education. It doesn't account for all the differences between individual data points, but that's why we have the error term. The error term accounts for everything else that might affect income. So holding everything else constant, how much would you expect your income to go up when education goes up? Well, the true relationship is beta 1, the slope of this blue line. But we don't know that true line. We don't know that blue line because we can't have all the data in the world to get that line. So what we do is we have to estimate it. We estimate a linear model. And now I've drawn a green line on here, a green dashed line, to give you an idea that, okay, we're going to generate some predicted linear relationship, some predicted linear function of income and education. All right, so this green line is the estimated linear model, and it's some estimate of the blue one. It's not perfect. It doesn't perfectly match the blue one, but it's some estimate of the blue one. It's some estimate of the true linear relationship. And the slope of this estimated linear function is beta 1 hat. So we call this beta 1 hat. That is the slope. That is the estimated slope. All right, so we use statistical methods to estimate beta 0 and beta 1. Once we have estimated the value of beta 0 and beta 1, we will use an estimated regression model. So now this is our estimated regression model. Here, income hat is the predicted value of income given, I did not change these enough, education. All right. So here, income hat is the predicted value of income given education. So we perform some some statistical technique, which we will go over later, we perform some statistical technique that allows us to estimate beta 0 and beta 1. So we get beta 0 hat and beta 1 hat. These are estimates of the true beta 0 and the true beta 1. Once we do that, we can plug in education and calculate a predicted income value. A predicted income based on our linear model. If this linear model was a really good model, if this was a really, really good model of explaining income, then you could go to some new population of people, ask them for their education, plug it into the model, and then you could generate a predicted income. All right, so this is our predicted, our estimated regression model. All right, this equation right here is this dashed green line. Every value on this dashed green line is a predicted income. It's an income hat given the value of education. The slope of this green line is beta 1 hat. And the place where this dashed green line would intersect, the place where this dashed green line would intersect the y-axis, that is when education would be 0, that would be your beta 0 hat. Okay. All right, so we never have all data for everyone in the population, so we can never have beta 0 or beta 1. But we can estimate them by finding beta 0 hat and beta 0 1, which is the best that we can do at knowing the true values. The biggest question in econometrics is whether or not our estimated beta 1 is a good estimate of the true beta 1. We want to know the true relationship. We want to know how much income will go up if you increase your education. We want to know the true beta 1. But we can't know the true beta 1. Instead, we generate a predicted beta 1, an estimate of beta 1, and then we will spend a lot of time in this class asking ourselves the question of whether or not that beta 1 hat is a good estimate of beta 1. We want to know whether the expected value of that beta 1 hat is equal to the true beta 1. We will devote a lot of time to that. That'll be very important. So we'll return to this throughout the course. Okay, so let's reinforce this. Again, why do we do econometrics? We do econometrics because we want to find out what beta 0 and beta 1 are. We want to get good estimates of beta 0 and beta 1. Beta 1 tells us what the effect of x is on y. That is, how does y change given a change in x? If education goes up, will income go up? All right, these are the things that we want to know. If education goes up, will income go up? That would be if beta 1 is greater than 0. Or does it go down? So that would be if beta 1 is less than 0. We want to know so basically we want to know the sign. We also want to know if education goes up or down, by how much does it go up? So if education goes up, by how much will income go up? So this would be the size of beta 1. So we want to know the sign. We want to know whether beta 1 is positive or negative. We also want to know the size of it. We want to know how big it is. You know, if I increase my education, if I go back to school for 1 year, how much will my income go up? If it goes up a lot, then that'll be worth it. I'll go back to school. And if it doesn't go up by a lot, then it's not worth it. I want to know the sign. I want to know, okay, if I go back to school for 1 year, will my income go up or will it go down? Because if it's going to go down, I'm definitely not going back to school. All right? Okay. So we want to find out what beta 0 and beta 1 are. We want to estimate them so that we can use that information, that's valuable information, to know the relationship between these variables. It'd be valuable information for anyone discerning whether or not to go to college, to know if your income will go up if you go to college. All right. The other thing we want to use econometrics for is to predict what y is for a different group of people or for the future. If we know what beta 0 and beta 1 are, or that is we have good estimates of beta 0 and beta 1, we can predict how much people will make by only knowing their education level. That's, of course, assuming we have a good model. Okay, we'll talk about that later. So this is the power of econometrics. We can predict the future. We can predict what would be the case in other places or among different people. We can know the relationship between things, and we can use that to develop policy. What's the impact of having access to health insurance? That would be great to know that relationship. Let's say that we had a y, a dependent variable of disease burden. How often you get sick, and then x was access to health insurance. If you had health insurance, if we knew what beta 1 was, then that would have a big impact on policy. So if beta 1 was positive, that means if you have access to health insurance, your disease incidence goes up. Well, that would be really bad. Then we wouldn't want people to have health insurance. But if instead it went down, so that is beta 1's negative, so that is having access to insurance implies that you have lower disease burden. That means you get sick less often. Well, that's good to know. Then, okay, we really want people to have health insurance. And we might want to know the size. So let's say the size is really big, or it's a very large negative number. That means if you have health insurance, you have much lower disease burden. You get sick way less often if you have health insurance. Oh, okay, that gives us a really good reason to design policy that helps people get access to health insurance. Okay, so this is powerful. This is a powerful tool to be able to estimate the relationships between variables. We can use it to fuel policy and to make informed, data-driven, evidence-based decision making. Okay. All right, so I'm going to reinforce what I've just said. So estimation. So we also want to know things about beta 1. That's what we're most interested in. We want to know the relationship between our dependent variable and our independent variable. So namely, we want to know the sign. Is beta 1 positive or negative? If it's positive, that means the dependent variable increases when the independent variable increases. We want to know the magnitude. We also want to know the magnitude. That is, we want to know how big beta 1 is. Is beta 1 big enough? So we want to know how big of an impact the independent variable has on the dependent variable. So there's a typo. I'm going to fix this. We want to know how big of an impact the independent variable has on the dependent variable. We want to know how big of an impact education has on income. All right. We also want to know the significance. We want to know if the independent variable has a statistically significant influence or relationship on the dependent variable. Okay, now we just did the last lecture where we talked a lot about statistical significance. Statistical significance tells us whether or not some observed relationship has occurred by chance or is really a reflection of something true about the population. All right, so we also want to know whether or not our beta 1 is statistically significant. All right, so we're going to discuss that next. All right, so we're actually going to do hypothesis testing when we do our regression analysis. All right, so we're going to do hypothesis testing with our regression analysis. Let's see what that looks like. So we want to know if there is a statistically significant relationship between the independent variable and the dependent variable. So simply put, we want to know if beta 1 hat is significant, if it is statistically significant. Okay, so to measure significance, we need to do a hypothesis test. So we're going to do a hypothesis test on beta 1. All right, so what does a hypothesis test look like on a parameter estimate? Let's take a look. To do a hypothesis test, we must state a null and an alternative hypothesis. All right, so our null hypothesis when we're analyzing, when we're looking at our regression analysis, when we are looking at our simple linear regression, Our null hypothesis is that there is no statistical relationship between the independent variable and the dependent variable. So in our example, this would be our null hypothesis is that there is no relationship between education and income. That's our null hypothesis. If there's no relationship between education and income, that would mean that beta 1, our null hypothesis is that beta 1 equals 0. All right? Our null hypothesis is that beta 1 equals 0. All right? But now we would expect that education would have some impact on income. Okay, so then we state our alternative hypothesis. So our alternative hypothesis is that there is a statistical relationship. So that is beta 1 does not equal 0. Okay, this is an alternative hypothesis. I got to correct that. All right, so alternative hypothesis is that there is a statistical relationship. There is a statistical relationship that beta 1 is not equal to 0. Okay, now this is important. This is very important because when we do this analysis, when we create our estimate of beta, that estimate of beta, that number could be all manner of numbers, okay? But that number will almost never be 0. It'll almost never be 0. But the question is that beta 1 not 0 by chance? Or because it reflects a real difference from 0. That the true beta 1 really is greater than 0 or less than 0. Or does whatever we observe, is it different from 0 just by chance? Okay, so let's take a look. Now what do we do? How do we do this? To formally test the hypothesis, we use a t-statistic and a t-table, just like before. All right, but now our t-statistic is our estimated beta 1 hat minus the beta 1 of our null hypothesis. So that means beta 1 equals 0. So really this would be beta 1 hat minus 0, okay? Divided by the standard error of beta 1 hat. The standard error, again, is the standard deviation of beta 1 hat divided by the square root of the sample size. Okay, so this is just like hypothesis testing that we did in the last lecture. This is why it's so important to understand hypothesis testing. Why we took so long on it in the last lecture. It's because we do hypothesis testing every time we run a regression. We are always interested in knowing whether or not the beta 1 hat that we observe, that we estimate, is statistically significant. Whether or not we can reject the null hypothesis that it actually equals 0. It's hugely important. All right. So then we look up our values on the t-table. All right. So we went through pretty detail in last lecture. I'll move forward. Okay. So if beta 1 hat is not statistically significant, then we assume that it is actually 0, no matter what the sign or the magnitude is. Okay, let's just remember, what do I mean by statistically significant? What I mean is if I have evidence to reject the null hypothesis, then I would say it's statistically significant. So if I have evidence to reject the null hypothesis, that would mean that I have reason to believe that beta 1 is not equal to 0. Then I can say that my beta 1 hat is statistically significant. But if I fail to reject that null hypothesis, then beta 1 hat is not statistically significant. And if beta 1 hat is not statistically significant, then we assume that it is actually 0, no matter what the sign or the magnitude is. So in practice, we know if the coefficient is statistically significant by using our statistical software. So we'll just demonstrate this using Stata. We're not going to calculate this by hand. We're going to calculate it using Stata. All right, now let's take up one more topic before we jump into Stata and do our first regression. All right, let's look at the topic of what's called goodness of fit. So here again, we're taking up the question of whether or not we have a good model. do we have a good model of income? And reminding us, okay, we know whether our model is a good model by how well it can describe real data. Does our model really describe differences in people's income? Okay, and we use measurements. There are measurements. There are ways of measuring how well our model matches or describes real data. And we call these measurements goodness of fit measurements. And we're going to discuss one of them in this lecture, and we'll discuss another one of them in the next lecture. All right, so the most common goodness of fit measure that we will use is called R squared. This is the most common goodness of fit measure. It's called R squared. R squared is a number between 0 and 1, and it indicates how much of the dependent variable is explained by the independent variable. A model with a higher value of R squared is a better model for explaining the dependent variable. Okay. Now, in a future lecture, I'm going to go through and we're going to talk about how do you calculate R squared and what is R squared. But for right now, we're grabbing the intuition. Okay. So R squared is a number between 0 and 1. And the higher R squared is, the better the model is at describing or explaining the dependent variable. So in general, we like models that have a higher R squared. Although, as we'll see later in the class, R squared is not everything. So, but we'll get to that. All right. Now, with all of that said, we've done a nice intuitive explanation of what regression analysis is, of what econometrics is. So let's jump over into Stata and let's do some analysis. All right. So I'm going to open up Stata. I'm going to open up Stata. Here we go. And I'm going to open my do file, put that over here. I'm going to open up my data set, and let's see here. I'm going to open up my data set. I'm going to use wages to data. That's what I typically use in my illustrations. All right, so let's see, what are we doing here? Lecture number 3. All right, lecture number 3 is Introduction to Econometrics. Okay. Now, what do we want to do here? What do we want to look at? Now, let's say that in this illustration, we are going to look at the exact same questions that we looked at in the last lecture. If you remember in the last lecture, we were interested in knowing, we basically wanted to know what is the relationship between wage and education. That wasn't exactly the question, but that's basically the question. We might phrase the question a different way, and that is, do wages increase as education increases? Okay, so we're going to ask ourselves that question. And we're also going to ask ourselves the question, the same question we asked before in the last lecture, is do our wages higher for people working in manufacturing? All right, so we're going to ask ourselves these two questions. But now, last time what we did is we did mean differences and mean t-tests. That was a really useful thing, and we'll do that again throughout the course. It'll be an important thing to do when we're writing papers. But now we're going to look at this. We're going to study this using a regression. Okay, we're going to look at the statistical relationship between wages and education using a regression. But now first, before I run a regression, or oftentimes before I run a regression, there's something that I want to know. I want to get some intuition as to what I think the effects will be, what I think the relationship will be. So the first thing that I like to do is I like to get an idea. I like to get an idea of the statistical relationship, and so I like to plot I like to plot a graph. I like to plot a graph of income versus education. All right, so I'm going to do that, and we're going to use a scatter plot. This is exactly what we saw in the lecture. We saw a scatter plot, all right? And our scatter plot is going to plot income versus, okay, I'm sorry, it's not income. It's wage versus EDUC, or education, all right, graph wages versus education. So let's do that first. This is going to give us some intuition. This plot is going to help us to think, okay, do I think that there is a relationship between wage and income? Okay, so here we go. We've got our scatter plot. It doesn't look entirely different than the one that we showed in the lecture. We have on the y-axis here, we have hourly wages, and on the x-axis, so y-axis, hourly wages, x-axis is education. And we see all of the different value points in our data set. So each dot is an individual. This individual has 0 education, and they make about $4 an hour. This individual has maybe, let's say, 16 or 18 years of education, and they make $25 an hour. Okay, so each dot is a particular data value. All right, and now as we look at this graph, as we look at the scatter plot, do you think that wages increase as your education increases? As we look at this, do we think there's any trend? Is there an upward trend in the data? Is there some trend in the data where we would expect that on average more education implied greater wages? Do you think there's an upward trend? When I look at this, I think that there is. You know, if we think about, there's not very many data points out here, so it's hard to really make much judgment from out here. But let's take here. There's a lot of data here. For people that have about 7 years of education, their education is no higher than $10 an hour. But if we come up here, this person has, let's say, 12 years of education. Yeah, there's a lot of people here, but we also find people that have higher levels of education, as high as $22 an hour. If we come up here, okay, this person, 18 years of education, there's not a lot of data points down here, and there's a lot more up here. So when I look at this, I think, yeah, you know what? I think that there's a small upward trend where more education implies higher wages. Okay, so I like to generate a scatter plot. I like to generate a scatter plot and get some intuition about whether or not there really is an effect in the data or a relationship in the data. All right, good. So now that we've done that, we've gotten an idea. Whoops. We've gotten an idea. Now let's run our regression. All right, so now we've gotten our idea. So now we're going to run a simple linear regression. All right, and our simple linear regression is going to be wages equals beta naught plus beta 1 times EDUC plus an error term. Right? That's our regression model. How do we implement that in Stata? So Stata is a nice statistical package. What this is going to do is it's going to estimate what beta 0 is and beta 1 is given the wage data that we have in here and the education data that we have in here. And it's actually really straightforward. We just write reg is short for regression, and then we put our dependent variable, and then we put our independent variable. And that is it. So we run that. Boom. And here we go. This is our regression result. All right. Here is our regression result. We've regressed wages. We've regressed wages on education. So yeah, that's a language that you'll hear me say, is we have regressed the dependent variable onto the independent variable. We've regressed wages on education. Okay, and here are our results. All right, now we can go through these results section by section to talk about what all of this stuff means. Okay, so I want to do that, and I'm actually going to do that in the lecture notes because I have prepared this in advance. Okay, so you'll see here is our regression result, reg, wage, education. Okay, and so now what we're going to do, I want to go through this step by step and show you what everything in this Stata output means, okay, because there's a lot of stuff going on here. We want to make sure we understand it. All right, so let's go through this step by step. So you're looking at your Stata regression results, and the first thing we want to see is our dependent variable. Our dependent variable is given right down here. We know our dependent variable is wage, and the results show what our dependent variable is, and it's right here, wage. All right. Then we also want to find where's our independent variables. Our independent variables, that's down here. That's these two. Our independent variable that we put in the model is education, and then Stata automatically includes an intercept term. It automatically includes a constant, okay? So we don't have to put a constant into the regression. It automatically has it there. All right. So then we want to find where are our regression coefficients? Where are our parameter estimates? Well, that is the next column, all right? It says coef, C-O-E-F, coef. That's short for coefficients. All right, so this number here is the coefficient on education. That means this is beta 1 hat. This is our estimated beta 1. This is the estimated relationship between wage and education. This is beta 1 hat, our estimated value, our estimation of the true relationship between wages and education. And then this one, this is the coefficient on our constant term. That means this is beta 0 hat. This coefficient right here is beta 0 hat. All right, let's go to the next one. Now, the next one, what you'll find is, and you'll remember from hypothesis testing, that having a standard error is really important because you need to be able to calculate a t-statistic to test your hypothesis. Okay, so this reports your standard error. This is the standard error of your coefficient. This right here, this is your standard error for your beta 1 hat. The standard error for beta 1 hat is right here. The standard error for beta 0 hat is right here. Okay, standard error for beta 0 hat here. Standard error for beta 1 hat is here. All right, now, if you remember actually, let's go up and remind ourselves. So if we want to do a hypothesis test, we state a null hypothesis. That is that beta 1 equals 0. That's our null. Our alternative is beta 1 does not equal 0. Okay. And then we test that using a test statistic, a t-statistic, where you do your beta 1 hat, the beta 1 hat that you observe, minus your null hypothesis beta 1, which is 0. Okay, so it would be beta 1 minus 0. That means it's just beta, divided by the standard error of beta 1 hat. Okay, the standard error of beta 1 hat. All right, so where the standard error is the standard deviation divided by the square root of n. All right, so that's just a reminder. Let's come back to our regression. We have the standard error. Now we want to know what is our t-statistic. Well, before we move on, let's calculate it. Let's calculate it. All right, I'm going to get out my calculator. I'm going to get out my calculator here. And now I just showed you that the t-statistic for beta 1 hat, the t-statistic for beta 1 hat is the coefficient is beta 1 hat, so 0.5447, we'll round it off a little bit, divided by the standard error, okay? So that would be divided by 0.0534. What? 53, okay, let's round it up 5. Okay, that equals 10.18. All right, that's 10.18. That is our t-statistic for beta 1. Let's look at our Stata output. All right, next column. Stata gives us our t-statistic, so we don't have to calculate it. The column is titled T. That stands for t-statistic. All right, and what did we find before? We found that the t-statistic was 10.18. Okay, well, we did some rounding. If we calculate it precisely, the t-statistic would be 10.19. All right, coefficient divided by the standard error. That gives us our t-statistic. We also have a t-statistic for beta 0. All right. All right, now, pausing there, think back again. We want to test our null hypothesis. Our null hypothesis is that the true beta 1, the true relationship between wage and education, is 0. That's our null hypothesis. And so now we're performing a t-test to test that hypothesis. Now, if you remember from last lecture, what we typically do is we find our p-value. That is, we find the probability of observing a t-statistic greater than or equal to the t-statistic that we find. So we find the probability of that. Okay, and if that probability is smaller than our predetermined, our chosen, our selected significance level, then we reject the null hypothesis and we conclude that our beta 1 hat is statistically significant. All right, so we need to find our p-value. Well, Stata is so nice, it gives it to us. All right, here is our p-value. This is our p-value for education, for the education variable, for beta 1 hat, and this is our p-value for beta 0 hat. All right, the p-value, assuming the null is true, the probability of observing a coefficient at least as extreme as the one that we observed. All right, now let's review. Thinking back to last lecture, the significance levels that we would typically choose would be like 0.1, that would be a 10% chance of type 1 error, or 0.05, that would be a 5% chance of type 1 error, or the strongest one that we would typically pick would be 0.01, 1% of type 1 error, 1% chance of type 1 error. Now, if we look at this p-value for beta 1, we find that it is 0.000. That means that our p-value is smaller than any of our thresholds. It's smaller than 0.1, it's smaller than 0.05, and it's smaller than 0.01. That means that we can reject our null hypothesis and conclude that beta 1 hat is statistically significant. That means we have evidence, we have reason to believe, we have evidence to suggest that beta 1 is not equal to 0, but in fact is some number larger. We have reason to believe that this coefficient, 0.544, that this coefficient is not actually equal to 0. That it's not just by chance that it's 0.454, but in fact that it reflects a real relationship between wages and education. Statistically significant. There is a statistically significant correlation between wages and education based on our hypothesis testing. All right, so it's very nice. It's all reported right there. Now, one thing that's going to be very important for you when you're producing results tables, and important for me, something I really want to impress upon you, is to produce high-quality, professional-looking tables. All right. So what you'll do is you take these results and put them into a nice table, something that looks like this. All right, table 1, you got a label on it, table 1, and then some name that describes what the model is. You've got the dependent variable over here. You've got the independent variables here. You even indicate the unit of measurement. So wages is measured in dollars and education is measured in years. All right, and then you present your model, so model 1. And the coefficient, your beta 1 hat, your coefficient on education is 0.545. Your coefficient on the constant term, your beta 0 hat is negative 0.934. Okay? And then you report using stars the significance level. All right, and there's usually a key down at the bottom to indicate what the stars mean. All right, if your p-value is less than 0.1, you'd give it 1 star. If it's less than 0.05, you give it 2 stars. And if it's less than 0.01, you give it 3 stars. We noticed in our results that our p-value for beta 1 hat, that means the coefficient on education, was 0.000. That means it's less than 0.01 and it deserves 3 stars. That means it's highly statistically significant. We have very good reason to believe that that number is not 0. We have very good reason to believe that there is a statistical relationship between wages and education. Okay, but now what about the constant term? All right, the constant term has a p-value of 0.175. So let's come here. I've got the constant term. Look at this. I've got 3 stars on it. All right. We only give 3 stars if the p-value is less than 0.01. All right. So it doesn't deserve 3 stars. What about 5 stars? I'm sorry, 2 stars. Is it smaller than 0.5? No. Okay. It doesn't deserve 2 stars. What about, is it smaller than 0.1? No, not smaller than 0.1. Okay. Then this should not have any stars on it. So let me delete the stars. That coefficient is not statistically significant. That means we cannot conclude that beta 0 hat, our predicted beta 0, we cannot conclude that that beta 0 hat is not 0. That means we would actually conclude, we would look at this number, and even though the number is negative 0.934, we would actually say that that number is actually 0. That in reality, we think our data suggests that it's 0. That there's no that basically if education equals 0, wages equal 0. All right. Now we also report here in a good, well-formatted, professional-looking table. We're also going to report some other information like the R-squared, the goodness of fit measurement, which in our case is 0.1654. I'll go into more detail about that in a moment. And we also we want to report the sample size, n. So we have 526 in our sample. All right, so that's what a nice looking table looks like. I want to see nice looking tables when you present your results. All right, now let's review again. How do we interpret this estimated coefficient? We've just calculated an estimated coefficient. It's 0.545. That's the estimated coefficient, estimated beta 1 hat. How do we interpret that? Beta 1 hat is the change in y given a unit change in x. So in our example, here's our beta 1 hat. As long as beta 1 hat is significant, then I would say wages increase by 54 cents per hour for each additional year of schooling. That's how I would interpret that coefficient. Wages increase by 54 cents per hour for each additional year of schooling. All right. Now, if beta 1 hat is insignificant, then I would say I do not find evidence that education is related to wages. I basically have to I fail to reject my null hypothesis. If I fail to reject my null hypothesis, that means I don't have evidence to suggest that beta 1 hat is not, or that beta 1 is not equal to 0. And so I have to say I do not have evidence that education is related to wages. All right, I want to make this even more clear. Basically, beta 1 equals the change in wage given a change in education. But this is if and only if no other factors are changing when I change education. So I'm assuming when I interpret it that way, I'm assuming that when you increase education, that does not change anything else. All right, so I'm describing that here. So that an increase, a change in education does not induce a change in anything else. And if you remember, our error term accounts for all other factors. So if when I increase education, I do not increase any other factor, then that means that the change in epsilon given a change in education equals 0. So when I say that beta 1 hat or beta 1 is the increase in wage given an increase in education, or the change in wage given a change in education, I am assuming that education does not affect anything else in the in the model. Now, this is going to be very important. We're going to talk about this more later. So when we interpret beta 1, we are assuming that nothing else in the model is changing when we change, not chance, when we change education. All right. Now, let's take a look at our goodness of fit measures. So in our Stata results, we also get goodness of fit measures. This describes for us how good our model describes the data. How well does our model describe changes or variation in wage? We've got two that we're going to focus on primarily. They're called R squared and adjusted R squared. We'll talk about adjusted R squared in the next lecture. So for right now, let's just look at R squared. Our R squared is 0.1654, and we report that in our table, 0.1654. Now, I said earlier in the lecture that the R squared is some value between 0 and 1. Some value between 0 and 1, and the higher that number is, the better. The higher that number is, the better our model explains the data. And I said, we kind of know how good our model is by knowing how well it explains the data. We have an R squared here of 0.165. That's kind of close to 0. That kind of makes us ask ourselves a question. Can we think of a better model? Can we think of a model that explains wages better than just a model of education? What other factors might affect wages? Think about that until next lecture. Thanks, everyone, and have a great day.